All right, welcome to Mikayla Huffman's Physics Honors Defense.
Ooh, okay, I'm gonna start my timer. All right, hello folks, my name is Mikayla Huffman, and today I'm gonna be talking about my thesis, the investigation of tertiary impact cratering and its relation, hello Autodesk, to impact physics theory. So to start off, these are the tertiary craters we'll be talking about, but before we even get into that, I'd like to thank some folks, obviously everyone in this room, and on Zoom, and Kelsey, who's also on Zoom, Professor Scher, Rowan, and Professor Armstrong. Thanks, guys, for being here. All right, let's get started. So first, I'm going to tell you what I'm going to tell you about. We're going to talk about theory, how I process and analyze the images of the moon, secondary craters, tertiary craters, a little bit of the code I wrote, and some conclusions and future work, because what kind of a science talk would this be if I didn't talk about conclusions and future work? So first I said I was going to tell you about theory. So let me tell you about theory. So when you think of an impact event, you're probably thinking of the primary crater. Big rock or ice ball comes down from space, makes a big hole in the ground. And primary craters are super useful for geochronology. Geochronology is trying to figure out the age of surfaces. And since the incoming rate of impactors or projectiles is more or less constant throughout geologic time, if you count all of the primary craters on a surface, you can estimate the age of the surface, back calculate it. Well, one problem is every primary crater is going to throw out some ejecta, which can re-impact the surface, creating thousands of secondary craters for each primary impact. If you were to count all of your secondaries as primaries, you would severely overestimate the age of your surface. That's a problem. So it would be super useful to have some sort of an equation that would say, okay, at X kilometers from a primary crater of Y size, the biggest secondary we would see is Z meters. That's what Kelsey and I have been working on for the past couple of years, and I do contribute to that a little bit in this work as well. In addition, secondaries are useful for some things. They give us a record of the impact cratering process, which is hard to study on Earth, which is probably good because you don't really want a planetary-sized impact smacking into Earth every few thousand years that we could study. So the majority of our information about impact cratering comes from planetary data, which is hard to study because it's not on Earth, terrestrial rigs like the vertical gun at NASA, which can get up to a couple of kilometers per second, but still that's kind of slow for some of these larger impacts. And then also from field work, which is basically going out and looking at craters made by military operations. And we don't really want more of those either. But luckily, secondary craters give us a record of the impact process. The distance of the secondary from the primary is related to the velocity of the fragment that made it. And the size of the secondary is related to the size of the fragment that made it. I'll actually walk you through the math in a little bit. But these equations, because of how they're derived, which is from typically momentum transfer, basic kinematics, it's only supposed to apply to very large, very fast, very high energy impacts, hypervelocity ones. But in theory, secondaries could have their own secondaries, tertiary impact craters. These would be very small, slow, and low energy, because the largest secondaries are about 4 to 6% the size of their primary. So we're talking 6% of 6%. These get really small, really fast. And during this kind of impact and then ejection process, you're losing a lot of energy. So these would be small, slow, and low energy. So maybe we can compare this theory, which is for very fast, very large, very high energy things, to these small, slow, low energy craters. They've been mentioned in the literature, but it's mostly speculation. But we've actually looked for them. And spoiler alert, we found them. But first, a quick detour. How do we actually distinguish between secondaries and primaries? I stole these pictures from Kelsey. These are secondaries around Copernicus, which is a crater on the moon. And there's a few characteristics that some secondaries have. They might have V-shaped ejecta, so you can see this nice wing right here. They can have a splatty or poorly defined downrange rim. So this is the direction to Copernicus. And you can see this uprange rim is more sharply defined than the downrange one. They can be elliptical with their long axes pointing back towards the primary. And they can occur in chains, clusters, or bright rays. You can see this type of material has a higher albedo than the surrounding one. Now, not all secondaries show these characteristics, and there are inevitably going to be secondaries that we miss. But luckily, due to our methods, which I'll get into in a bit, we don't need to see every single secondary. We just need to see the largest ones. Okay, here are some more examples of some secondaries and some primaries. Here I'll put some things on it. So these guys are secondaries because you can see that V-shaped ejecta right there. This one has nice V-shaped ejecta, poorly defined downrange rim. This is a primary. You can tell this is a complex crater because it's got that guy on the inside. This has that V-shaped ejecta right there as well. You can see that they're kind of clustered together. This one, although it is elliptical, is not a secondary. And you can see that it doesn't really have that V-shaped ejecta. In addition, this was a highly elliptical primary impact. It is very hard to make ellipses that extreme for primary craters. And it pretty much probably bounced into that hole. This is also a primary. You can see they don't have to be complex. They can be simple. Complex craters tend to have more rings. Then this chunk of secondaries is in a chain. Take a look at that scaling. So secondaries can be larger than primaries, but they are not larger than the primary that produced them. Okay, well, you may be thinking, well, Mika, you're having a bunch of different people map these secondaries. How do you know that I'm not going to get the same thing that Kelsey does? Well, a student who's working on our project had all of us map this northeast quadrant of Tycho crater, which is right here, and for secondaries. And he found that there's good agreement in secondary crater mapping, parameters within 95% confidence intervals, as long as you have a large sample size of secondaries. And we, let me tell you, did a large sample size of secondaries, over 8,000 for this primary crater that I'll be talking about. And the higher a sample size you have, the more confident you can be in this parameters. Okay, so let's talk about some math because this is a physics thesis. Remember how I said that the distance from the primary to the secondary is related to the velocity of the fragment that made it? Well, there's two equations that are really helpful for figuring this out. The first is the Habersign formula, which was originally made to make navigation on ships a lot easier. And so you have the input of a latitude and longitude coordinate pair for 2 points, A and B, on a sphere. You also have the impact or ejection angle theta, which goes into here, the radius of the sphere, which is the moon, and the gravity of the body, which is G. So this big guy right here is A, and that plugs into this formula. This gives you the distance on a sphere. And this is a lot more accurate at smaller angles than just mapping on ArcGIS does. So other equations that calculate the geodesic distances can mess up a little bit at smaller angles. And then we take this D along with some of the other parameters I described above and plug it into this equation, and you can get the velocity. Note that I said impact and ejection angle. We assume that the impact and ejection angle are the same because the moon doesn't have enough of an atmosphere to slow things down considerably. It has an exosphere. And out we get the ejection/impact velocity. All right. So then we also have this other equation, which gives us the fragment size that produced a crater of a given diameter. This is typically the minor axis for ellipsoid craters. And these are the Schmidt-Holsapple-Housen scaling relations. So first I'm going to explain this plot, which gives us these two regimes, gravity regime and strength regime. The gravity regime is for impact craters where the gravity is dominant. So they're so large or so fast that gravity's effects overwhelm the material properties of the surface. For smaller or slower impacts, the strength regime dominates. This is gravity scaled size, so G is the gravity of the body, A is the diameter of the crater, and U is the velocity. And then up here we have the cratering efficiency. So it's the mass that used to take up the space that is now the crater, which has been displaced, divided by the impactor mass, so the mass of that projectile. Then we see the strength regime down here and the gravity regime over here for a bunch of different surface parameters. We are going to be in the strength regime because of how small and how slow our craters are. Okay, well, that gives us these two equations here. Now that we know that we're in the strength regime, we're going to use these two end member materials, hard rock, which is basically hard non-porous rock, and regolith. Lunar regolith, think about it like a little bit of sand with a little bit of yield strength to it, so it's not just friction forces. And the input, we have the diameter of the crater, the impact/ejection angle, again, those are the same, and the impact velocity that we calculated previously. This is for hard rock, this is for regolith, and out we get the diameter of the fragment that produced the crater. Note that the only difference between these equations is these parameters here. These are experimentally derived, so we need to check them. And this estimate of the fragment diameter is actually super useful because for secondary craters, you don't typically see the downrange projectile. It gets fragmented or vaporized or melted away. So we need to estimate the size. All right, now there are some limitations to these scaling relations, and I talked about this a little bit earlier, but they're only supposed to apply to large, fast, high energy impact crater cases. They're supposed to apply to hypervelocity impacts, where the speed of the impact is greater than or equal to the speed of sound in the target. And they're supposed to apply to ones where the mass that the impactor displaces is greater than that of the projectile itself. So basically, you're making a bigger crater than the projectile. But tertiaries are small, slow, and low energy. So does this theory still apply, even though it's not supposed to? Good question. And then I was talking about how there's that ratio between the displaced mass and the projectile. So here's how we actually calculate that. So we have this half ellipsoid here, which is the crater. And we can measure the long axis A and the short axis B just by looking at the map. But how do we get something about depth? The digital terrain models that we have are not very, you won't be able to see these craters on there. The digital terrain model global mosaic has a pixel size of about 100 meters. These we're talking very small, like 10 meters across. So you just can't see them. So how we get at depth is by looking at shadow measurements. So if on the surface, we know the angle the sun was at, and we can measure this distance, the distance of the shadow, L, then we can do a little bit of trig, I know, scary, to get the depth, which is C or D here. And then from that, we can calculate the volume of this half ellipsoid here. And then we see the diameter of the boulder, so we can approximate it as a sphere, like a good physicist, and get the volume of that too. So then we can get this ratio. Now you may be saying, well, we were talking about mass earlier. We're going to assume that the density of the surface, the target, and the density of these projectiles is the same. So that just cancels out. So if this ratio is 1, the volume of the projectile is equal to the volume of the displaced material. They're the exact same. The projectile made a crater that's the exact same size as itself. If it's greater than 1, then the projectile displaced more volume than its own volume. And this is when the scaling relations are supposed to apply. If it's less than 1, the projectile's volume is bigger than the dent that it made. Okay, so now let's talk about image processing and analysis. This is kind of a methods section. So if you guys want, you can pull your phone out. I have a little map on the Lunar Reconnaissance Orbiter camera's quick map that has a bunch of these craters marked. So I'm using high resolution imagery from the Lunar Reconnaissance Orbiter camera's narrow angle camera. This is a satellite that's orbiting the moon. It's American, and it has a pixel size of less than 1 meter per pixel. Very good resolution. And in this work, we present a potential set of tertiaries from a small 1.8 kilometer diameter, fresh primary crater to the south-southwest of Glushko crater on the moon. That takes a really long time to say, so I'm going to call it Wallace. We are working on naming it.
What does fresh mean?
Fresh means relatively young, so high albedo. We're talking instead of hundreds of millions of years, tens of millions or a couple million. So geologically recent. So initially I searched using the wide angle camera global mosaic. This is 100 meters per pixel, so very big. And also the NAP, which is the smaller imagery on the LROC quick map. So I basically panned around and looked at some craters. Then if we found imagery that seemed pretty nice, then we would put it into the USGS integrated software for imagers and spectrometers. This is a very sad acronym. So then we did some analyzing and mapping in ArcGIS Pro using geodesic distances. So we are working on a sphere. And we use the WAC predominantly as context for the NACs, which are that better imagery. And we mapped the potential tertiaries on the NACs. This right here is LRO. And then this over here is a GIF of me zooming in on the quick map. So we do have very good resolution on them. Okay, so initially I looked around larger, relatively young primaries, thinking about that 4 to 6% rule. If we're taking 6% of 6%, if you have a bigger primary, you're more likely able to see those tertiaries. But even on the relatively young large basins, including Petavius B, Tycho, Giordano Bruno, and Oriental, their secondary fields have degraded significantly over time. So we didn't really find anything. So then Kelsey stumbled upon this article, well, really just a blog post from L Rock that said, whoa, look at this fresh crater. And we were like, yes, we will look at that fresh crater. So Wallace is about 1.8 kilometers in diameter. And here's the Latin long. And this is what it looks like. So we're to the south-southwest of Blushko crater on the moon. And here it is. And I have printed out, 3D printed, here it is. This is Blushko right there. And then down there, that little pink guy is Wallace. So there's that. And then I've zoomed in more. This right here is Wallace. And then I zoomed in even more with better vertical exaggeration. That is Wallace. That's north. So as you can see, just from the albedo, it is very fresh. And to orient ourselves, one of the lunar mare is to the northeast here. Okay, so let's talk about the mapping method. So this is a little diagram that I did. So first, here's an example of a secondary crater. You can see the V-shaped ejecta. And I put a line over the minor axis that's approximately perpendicular to the direction to the primary. In yellow, that's the secondary. And then we have two different types of tertiaries. This one is just a blue line. But for ones that have downrange projectiles, so we want to be able to calculate that projectile versus the displaced volume ratio, then I did those shadow measurements that we talked about earlier. So you can see that red line showing the shadow. And then I also did the short axis and the long axis, which are perpendicular to each other. So here's some examples of me applying that. This is some secondary craters around Wallace, and this is the same exact image, just without the lines on it. And there is an example of some mapping. This is the final completed map around Wallace. Take a look at this sample size. Kelsey and I mapped 8,286 secondaries. So that is a very large sample size. Some of the other ones are closer to 1,000. This is very well mapped. And this NAP pair, so the right and the left, had the best resolution. So that's why we mapped up and down it the most. This one over here didn't have as good resolution, so there's fewer craters there. Okay, so here's an example of tertiaries. This is a little bit wonky looking. So the red lines are just extensions of the V-shaped ejecta of the secondaries, which are in yellow. If we zoom in here, you can see my examples of mapping the projectiles, which are in purple, the minor axes of the tertiaries, which are in blue, the long axes, which are in orange. This down here is the exact same image, but without the lines on it. So that's how I did my mapping. So here's a kind of a summary. To date, we've mapped over 8,000 secondary craters around Wallace. I got through a lot of podcasts. And we find a cluster of large secondary craters, 9.6 kilometers to the north-northwest. And around these secondary craters, 3 of them, which I will call Gromit, Cheese, and Wensleydale, there are 103 potential tertiary craters. And of those 103, there are 15 that we say are confirmed tertiaries. These ones are still possibly tertiaries, but these ones are, I'm like 95% sure they're tertiaries. These show the diameter of the secondary craters. So Gromit is the largest and Wensleydale is the smallest. Their locations and their distance to the primary. You can note that Wensleydale is outside of that little cluster. It's a bit further away. All right, this is my big figure. And we're zooming in. So you can see there's that lunar mare. Here's Blushko. There's Wallace down there. We're going 9.6 kilometers to the north-northwest. There's Gromit. This guy down here is Cheese. Gromit and Cheese. This is extensions of the V-shaped ejecta. The yellow ellipses are tertiary craters. The blues are projectiles that are downrange. And here it is without those ellipses on it. These are radial indicators from Gromit in green and from Wallace in red. You can see that they align more closely with the radial indicators from Gromit. I will talk about this figure more in a second. Okay. Sorry, I did a color change. Hope that woke you up. So now we're going to talk about the actual data. Let's talk about secondary craters. So first I have this plot here, which has the distance from the primary, Wallace's, center in meters. And on the y-axis, we have the secondary crater diameter. So each of these little dots is a secondary. So for example, this one is about 60 meters, and it's just a little bit over 5 kilometers out from the center of Wallace. This blue line here is the 99th quantile regression. So dots that are above this line are secondaries that are in the top 1% of their size for their distance from Wallace. You can see it's a pretty flat distribution, which is expected for small craters. And this is the equation over here. Now remember how I was saying it'd be super useful to have an equation like this? This equation basically tells us at r kilometers from a primary of, in this case, 1.8 kilometers in diameter, dW max is the biggest secondary we would see. So someone could go out and use this around another 1.8 kilometer diameter primary and map only above that limit, and then hopefully they'd only get primaries. So this can help with that geochronology problem. These are the parameters that we got. This is the one that parameterizes the diameter, and this one is the slope. And down here, I pulled some data from Kelsey's previous work. So this is a 3 kilometer diameter primary, 2.2 and 0.83. And then this one right here is Wallace. And as you can see, we are falling nicely in line with the pattern that's already shown. So yay, good sample size was worth it. Also on this plot, I have Gromit, Cheese, and Wensleydale as these orange points. Gromit is above that 99th quantile regression. Cheese is right below it, and Wensleydale is pretty far below it. Note, however, that Gromit is not like way over here. If it were, then we would say, okay, Gromit is definitely a primary. But there are still some secondaries that are in Gromit's size class. I will also talk about that a little later. All right. Well, in order for tertiaries to be tertiaries, they need to be secondaries of secondaries. So first, let's talk about whether these three tertiary progenitor craters are actually secondaries of Wallace. So I ordered them conveniently. Cheese is the most likely to be a secondary crater. It has all the characteristics of a secondary crater. Wensleydale is next likely, and Gromit is the least likely, but still is probably a secondary. So I'll walk you through that. First, let's talk about Gromit. Gromit is 3.3% diameter, the size of Wallace, which falls below that 4 to 6% rule, so it's not abnormally large. And it is similar to other secondaries in the area, but from that 99th quantile plot we saw, it is a bit larger than other ones in the area. So if Gromit isn't a secondary, it could be either a primary that overlies Wallace's ejecta, so Wallace came by and then later on Gromit happened, or a primary that was scoured by the Wallace impact and underlies Wallace's ejecta. So it came by and then the Wallace impact happened, giving it a scoured appearance. So let's walk through both of those. Is Gromit an overlying primary? No. But let me walk you through it. It appears shallower visually than the other primaries in red. Take a look at those shadow depths. It's elliptical with a poorly defined downrange rim. And there's ejecta inside of Gromit, these orange arrows, that is probably from Wallace. Or it could have just landed in a bouldery area and some boulders rolled in afterwards, but that seems less likely. And all of the elliptical dents that we're calling tertiaries are downrange of Gromit. So it would be pretty weird if all of these that we're seeing align better with the radial indicators from Gromit than from Wallace, and they just happen to be downrange of some unrelated primary. Okay, well, is Gromit an underlying primary? This is a little bit more likely than the overlying theory, but it's still unlikely. The tertiaries aren't scoured. They don't have a scoured appearance, but that could just be because they're very small secondaries of Wallace itself. It doesn't look like other scoured features in the area, here, here, and here, but it might just be because Gromit is larger. Gromit's rims are not as distinctive as other secondaries in the area, but that might be because Gromit occurred earlier in the Wallace impact process than other things, and so other ejecta came down on top of it. It does have this V-shaped ejecta that you can see here, and to our knowledge, a scouring process cannot produce V-shaped ejecta. It might just be that this V-shaped ejecta is scoured and it was already there before, but that would make this have to be a very elliptical impact. So it's unlikely, but not impossible. It is more probable that Gromit is a secondary of Wallace than an unrelated primary. Okay, well, let's talk about Cheese. Is it a secondary of Wallace? Yes, look at that guy. It's got the V-shaped ejecta. It's visually shallow. It's elliptical with the long axis pointing back towards Wallace. It's got this poorly defined downrange rim, and it's way below that 4 to 6% rule, which is why it's very convenient that there happens to also be a tertiary downrange of cheese. All right, what about Wensleydale? It's probably a secondary of Wallace. Here it is, right here. It's got that V-shaped ejecta. And you guys can see that knack difference, this imagery versus this imagery. It's visually shallow, it's elliptical with the long axis pointing back towards Wallace. It's got the poorly defined downrange rim. It's way below that 4 to 6% rule. And it is further out than cheese and Gromit. But again, remembering that 99th quantile regression plot, it has a very flat, Wallace has a very flat size distance distribution. So it is most likely a secondary of Wallace. Okay, now let's talk about tertiary craters. Well, are these tertiary fields of these guys actually tertiaries? So in this case, we're asking, are they secondaries of secondaries? Cheese is the most likely. Gromit's tertiary field is equally likely to be tertiaries as cheese's singular tertiary is, but because Gromit might not actually be a secondary of Wallace, I put it second. Wensleydale, they're probably not actually tertiaries. Yeah, they're probably not. They're more likely to be small secondaries of Wallace itself. Okay, so here's Gromit's tertiary field. This is the possible tertiary field on the left. You can see all those tiny little blue freckles. This right here is Gromit. These are other secondaries. And note how, for example, this tertiary might have come from this secondary or from Gromit. So we basically just said, okay, we're just not going to take any of them that overlap with the V-shaped ejecta of other secondaries. In addition, we also cut it down further by saying we're only going to take tertiaries that are greater than 3 pixels across. So that's 2.64 meters across. And that's how we went from this field of 76 to this field of 14. So taking a look at those, they're shallow, elliptical, and their long axes point towards Gromit. And again, you might be thinking, well, what if they're just very small secondaries of Wallace? Then it would be very strange that all of them align more closely with radial indicators from Gromit than with the radial indicator from Wallace. That would be very unlikely. In addition, they have these downrange boulders. Now, take a look at this one. It has 2 dents before the boulder. These are sort of in an intermediary regime between boulder trails that skip along the surface and leave a bunch of, like, think about skipping a rock across a pond, and actual secondaries, which is what we would expect for tertiaries. And again, they have downrange boulders. We don't typically see this for secondaries. So this is a unique morphology that we're finding here that will let us do more physics than with the previous generation of craters. All right, this is just a histogram. So frequencies on the y-axis, and the tertiary crater's minor axis length in meters is on the x-axis. This is n equals 18. And on average, they are about 5 plus or minus 1.5 meters along that short axis, which is about 8 plus or minus 2.4%, the size of Gromit by diameter. Note that the 4 to 6% rule, this is a bit large, but it overlaps with an uncertainty. And this is just a rule of thumb. So it might only apply to secondaries or larger impacts. Plus, again, we took the biggest tertiaries we saw, those that were above 3 pixels. So if we include all 76 potential tertiaries in Gromit's tertiary field, this number would likely be lower. So these are probably tertiaries. In addition, I would like to note this box. These are small, very small craters. We're talking meters here, not kilometers, not hundreds of kilometers. I'll get back to that in a second. Okay, let's talk about cheese's singular tertiary. It is similar in morphology to Gromit's tertiaries. You can see that elliptical dent that aligns very nicely with the V-shaped ejecta from cheese versus this is the direction to the primary. And it has a downrange boulder. This is the most likely of all of the dents to be a tertiary, which is why it's so awesome that cheese is definitely a secondary of Wallace. In addition, you can see Gromit up here. That's Gromit. All right, now let's talk about Wensleydale. This is the bad one of the bunch. So here's Wensleydale right here. And all these blue dots are potential tertiaries. And I've zoomed in on some of them here. The morphologies are dissimilar from Gromit and cheese's tertiaries. They just don't look the same. They're shallow, they have radial chains and clusters, so it's more similar to what you'd expect for small secondaries. And the real kicker is they're about 8 plus or minus 2 meters on average, which is 24 plus or minus 7% the size of Wensleydale. That's way above that 4 to 6% rule. So it's pretty unlikely, possible, but pretty unlikely that these are tertiaries. they're more likely to be small secondaries of Wallace itself. In addition, it's hard to put radial indicators on this guy because it's further out. So the radial indicators from Wallace would look pretty similar to those from Winslow. All right, so using the two tertiary fields of Cheese and Gromit, we're presenting this list of tertiary crater characteristics, just like those secondary crater characteristics that I defined earlier, but this time for tertiaries. We have an extreme elliptical shape with the long axis aligning more closely with the reductive secondary than with the primary. They sometimes have associated downrange projectiles, and those sometimes have boulder tracks leading to the tertiary. And that kind of whole system of the projectile and the tertiary, the long axis tends to be aligned more closely with ejection from the secondary than from the primary. And they tend to have a shallow depth with a small depth to diameter ratio. So using this list, you too could look for tertiaries. All right, so let's get back to those equations I talked about earlier. So we're going from the primary to the secondary. Stuff gets ejected out of the secondary and re-impacts, creating a tertiary. This red X, the impact velocity that forms the tertiary, is this histogram here, which I'll explain in a second. The outgoing velocity, which again is the same as the velocity that the projectile lands with, because we're assuming they're the same, is this plot over here. So on the x-axis, we have the velocity that formed the tertiary. And on the y-axis, these are just a bunch of histograms. The one difference between them is the angle. So red is 5 degrees, 10 degrees, 15, 30, and 45. Note that the 5 degrees is faster, because think about launching from 5 degrees. You have to go faster to make the same distance that a 45-degree projectile would make. Note that these are pretty slow. Also, it probably isn't 5 degrees and it probably isn't 45. It's more likely one of these intermediate angles. So we're talking like 20 to 30 meters per second. This is probing the lower limit of what we think will make a crater on the moon. Looking at the ejection, so this is coming out of the tertiary. It's the same exact type of plot, same angles. We just lowered the sample size because these are only ones that have projectiles. And we're getting down to like 5 or 10 meters per second. These are very slow for impact cratering. All right, now you may be thinking, okay, well, you have incoming velocity and outgoing velocity, and you already told me that you know how to measure the volume of the projectile. Yes, I've caught up, we're doing kinetic energy. So we can get the volume using this formula of the projectile. We can estimate the mass by using average density of lunar regolith. And then we plug that in here, and we have the incoming and outgoing velocity, and we can do kinetic energy change. So the kinetic energy that was lost during the formation of the tertiary crater. That's this plot here. So kinetic energy lost in megajoules is on the x-axis. And for taking, for example, 15 degrees, the average kinetic energy loss is about 25 plus or minus 20 large error bars megajoules, which is approximately equal to the explosive energy from 6 kilograms of TNT. And you may be saying, whoa, that's a lot of TNT. Well, Rowan, I put this in for you. The extinction event that killed the non-avian dinosaurs was about 23.9 million kilograms of TNT. So these are pretty low energy. So hopefully I've shown you that these tertiaries are small, slow, and low energy, which is similar to some terrestrial experimentation. Terrestrial rigs can produce several kilometers per second impacts, especially that vertical gun range. So we are squarely in terrestrial experimentation zone. In addition, I'm going to remind you that scaling relations are supposed to apply to hypervelocity craters with a displaced to projectile volume ratio of more than 1. So the projectile displaces more volume than its own volume. Well, does this actually apply to tertiaries, who are definitely not very large, very fast, very high energy impacts? And remember, these scaling relations allow us to predict projectile sizes, which typically, you can't look at the projectile for secondaries because it's gone. But we are seeing them downrange of tertiaries. So we can predict the projectile size using the scaling relations, then actually check it using the actual boulder sizes we see. So I do not know who this person is, but let's talk about the actual boulder sizes. So this is just a histogram showing the boulder/tertiary projectile size in meters on the x-axis. Boulders and tertiary projectile are the same thing. It's not division. And the average diameter is 3 plus or minus 1 meters, which is about the size of a Mini Cooper. So a Mini Cooper is about 4 meters long and 2 meters wide. So provides a nice comparison. And this translates to a volume of about 3.1 to 57 meters cubed. All right, so let's take a look at this plot. This is comparing the observed to the theory. So on the x-axis, we have the actual projectile diameter. So for all of these points, I went and measured the actual projectile diameter. These two sets of lines are predicted for the associated tertiary. They're predicted from the associated tertiary. So this is actual, the black line. These are two theory end member predictions. So the dashed lines are that hard rock surface, and the dotted lines are that regolith surface. This is the predicted, this is the actual. So this black line has a slope of 1. It's if the predicted perfectly matched the observed. So the red dots are those for which the scaling relations are super not supposed to apply because the displaced to projectile ratio is less than 1. So all of these are not hypervelocity, but these dots are also have the wrong quote unquote volume ratio. But look, all of our points fall between these two end member predictions. So the scaling relations apply to a broader range of impact events than we previously thought. And a quick note, even if all these guys aren't actually tertiaries, this conclusion would still apply. So if I haven't convinced you that they're tertiaries, then this still applies because it's for any small crater. All right, so remember on the previous couple slides, I said, do these apply to tertiaries? Do these scaling relations that are only supposed to apply to very big, very fast, very high energy things, do they actually apply to these small, slow, low energy things? Yes, because they match with the actual Boulder sizes that we see. We are providing a planetary data-based check on experimentally derived theory predictions. All right, I also did a little bit of coding. So first, let's talk about the primary crater code. So this is very useful because you can put in the diameters of primary craters and it will output a list of young, fresh primary craters that tertiaries would be resolvable around. So you say, okay, I have imagery that is 1 meter per pixel or 100 meters per pixel. And then you put in the diameters and then it filters out some of them. This one, I plugged in only very, very young primaries. And look, all 8 of them, you could potentially find tertiaries around. Note, however, this includes Tycho and Batavius B that I already looked around and didn't find them. But that was before I had that list of tertiary crater characteristics and before I knew where to look for them. I also wrote another code that's basically just a bunch of lists of functions that calculate the crater size, the range, the productive fragment size, and velocity for secondaries and tertiaries. So you can put in a primary and it will kind of output these things. And these tools help us in searching for more tertiaries. All right, let me summarize what I just told you. We conducted the first systematic search for tertiaries and found the first confirmed tertiary craters, 15 of them. We defined a list of tertiary crater characteristics, so you too can go out and look at the quick map and find them for me, instead of me doing it. In addition, we note their unique morphology. They have downrange associated projectiles for some of them, which is unlike secondaries. So we can do more physics with these tertiary craters than with secondaries. We also calculated the kinetic energy lost during the tertiary formation. We also tested the Schmidt-Holsapple-Housen scaling relations and noted that they actually do apply to much slower tertiary craters who even have the wrong volume ratio. So we provided an empirical planetary-based check on experimentally derived parameters that are used in these scaling relations. In addition, we're probing the lower limit of what will actually make a crater on the moon, as low as 20 to 30 meters per second. There are some people in the planetary world who might say, that wouldn't make a crater. Well, it does. And we produced some code that will help us in the future. So let's talk about that feature. So obviously I'm gonna look for more tertiaries around Wallace. And then I'm gonna look for more tertiaries around other primaries, especially small fresh ones. And we know that they appear in places with boulders. So I could simply look for places with boulders and then look around those using the tertiary characteristics that we've outlined here. In addition, I'm going to do more theory comparisons. It would be super cool to take that energy further and say, okay, well, how much would that actually displace or melt or vaporize, and compare it to other theory as well. Then I'm already working on this. Seth was helping me. I'm working on a machine learning algorithm to tell us where to look for tertiaries. So not to find them for us, but tell us where to look. And that's something that I'm already working on as well. Thank you.